and a sequence of that being the greenhouse phenomena and many aerosol radiative forcing that we have come across in recent times, and their importance for the Earth's radiation budget. So this is the scope for today's lecture. And if you permit me, I would like to share the screen straight away. And all right, now this is something extremely elementary, but nevertheless, let me start with this. What it says here is the Earth's axis, the Earth going around the sun. This diagram is far too beaten to be told with a legend. And if you look at the axis in all its positions around the sun, it's kind of frozen in space. And that is expected out of the dynamics if Earth was only born. Subjecting rotational axis to additional torque, and that may change the angle of this axis. But that is a slightly different issue, which I would not like to talk at length. But the first thing that you notice here is that this is in one of the two sides of the ellipse. Exaggerated. It's not so elliptic, it's almost circular. But this again, with time, keeps on oscillating, getting a little more elliptic at certain times and then becoming close to a circle at certain other times at very, very long time scales. All right, now this is the Earth all around. And don't say that this position on the right-hand side is the summer season for Northern Hemisphere. In fact, the sun is closer to it, because that doesn't determine what is summer and what is winter. What does determine is the angle with which the sun's rays strike the ground. Now, this perpendicular component of this radiation that is drawn here as a vector is the one that is causing solar insolation. And the one that is parallel to the ground is just grazing it, and it doesn't contribute. So obviously, it varies from whatever radiance you're getting from the sun. It varies between 0 and that value. So there's a huge difference. And if that happens from one day in the calendar year to another day, that's a very, very major influence on the amount of solar radiation that is being intercepted at a certain point. This small change in the distance hardly would give you that kind of a dramatic effect. And therefore, the seasons really don't depend upon the distance, and they depend upon the angle with which the sun is striking the Earth, the average angle for the whole day. Now having said that, we would say that this particular angle, the smaller it is, this is called the zenithal angle. This is the local vertical. So this is called the zenithal angle of the incoming solar radiation. Now, if you try to imagine over here, please remember one thing. I'll draw this a little bigger, and then it'll be easier for us to discuss. Normal incidence is at this point. Can you realize this? These are the grids, latitudes that have been drawn here. And the normal incidence is when the solar radiation extended would have gone to the center of the Earth, because there the surface, which is a tangent, would be perpendicular to it. So this is a point of normal incidence, perpendicular incidence, given this kind of a thing. Now, if this be the tilt of the Earth's axis, that means somewhere over here, this be the tilt of the Earth's axis in this particular position, if you look at it, the sun is normal at a certain southern latitude. This being the equator, this dark line being the equator heavy line, this particular lighter line is one of the southern latitudes. And therefore, it's perpendicular on this particular day. that can be seen on this diagram over here. And well, if that be the case, then let's look at the distribution. The distribution says that at this point, this latitude, the sun's rays are grazing the ground. In other words, further north of this, no radiation would be intercepted by the ground, and that's why we have a winter condition, a night condition there, right, over here. Also imagine the second thing is that if you look at the opposite side, this being the central line, point from here, anything that is rotating and that is passing from one longitude to the other on this particular latitude circle, as the Earth is rotating, entire duration will be sunlight hour, okay? So in this position, the southern hemisphere, anywhere on the southern hemisphere, gets the sunlight. And now let's look at something else also. The other thing being, if you look at this from here to here, the point would go around as it rotates and come back here, isn't it? So the point literally traverses along this line. So, point is the observer. That literally traverses along this line, and this from here to here is daytime, and from here to here is nighttime. So the shadow of the Earth itself is on the night side. There no light reaches there, and that being so, the length of the day is more than the length of the night. That is also expected. So this is summer season for the southern hemisphere. Exactly opposite happens when you look at this. Well, this is the same diagram. So when you look at this in a reverse way, that means when the Earth is positioned over here, the sunlight doesn't come from the left. The sunlight would come then from the right of this diagram. And then you would have the summer season for the northern hemisphere, the length of the day in the northern hemisphere being more than the length of the night. Okay, the length of the day is the time taken to traverse along this latitude, okay, from this point to this point. So this is pretty obvious. And these essential aspects of the solar radiation versus the Earth's tilt is important in defining seasons. Now, just try to imagine as a mental exercise that this is northern hemispheric winter and this is northern hemispheric summer. So this distance, whatever minute be the difference, would mean what? That the northern hemispheric summer receives less radiation, a little less radiation than the southern hemispheric summer, and vice versa. Now, this is the fact of life, that the northern hemispheric summer receives a little bit of extra radiation than the northern hemispheric winter receives a little less radiation than the southern hemispheric winter, and vice versa. What it has on the climate is not to be felt in a century scale, but over millennia, the small difference between the northern hemisphere and the southern hemisphere, that shows up in the form of certain oscillations. Well, having said that, we have seen a diurnal variation of solar insolation, the diurnal being a movement from day hemisphere to the night hemisphere. Then we have also seen, as it goes around over here, we have also seen how the seasons change and what is the nature of that season. We have noticed that. But there are very, very slow changes in the axis and in the angle of the axis. And these are caused by the gravitational effect of nearby heavenly bodies, principally the moon and certain other planets. As a result, mathematically, you can explain that as separate kinds of motion exhibited by the Earth's axis. One is a precession, and this is also a pretty slow process, the precession. The other is the oscillation of the extent of inclination. Now, this inclination you are used to saying is 23.5, but it can get a little less, a degree or so less, and a degree or so more than that. We are somewhere in the midpoint today. So, well, it oscillates. Suppose it becomes a little more vertical than it is today. Today it is inclined at 22.5, and suppose it gets a little more vertical today, then what will happen to the points where the sun reaches the zenith at least once in a year? These are the two latitudes. Beyond this latitude, the sun will never reach the zenith during the entire day. And similarly, this is the north. And the north one, Tropic of Cancer and the Tropic of Capricorn, this latitudinal difference, this part of this globe defines what is tropics, where the sun comes overhead at least once. At least once in a year. It wouldn't do that if you go north of that or if you go south of this. So that is the definition of the tropics in one particular way, in an astronomical way. There are many ways to define the difference between the tropics and the extratropics. One of them being the diurnal variation being bigger than the annual variation in the tropics. The other being the kind of weather that you see in the tropics. There are various ways of looking at the definition of tropics. But the most convenient way is to see the Hadley cell. That is the extent to which the Hadley cell would extend. That is important. So that defines the subtropics, where the air descends over those regions on either side of the equator, and it ascends on the equator. So there are many ways of defining the tropics. This is one of the ways in which at least the sun comes overhead at least one day during the entire year. Now, so what will happen if this angle of inclination increases? Okay, if this angle of inclination increases, what will happen? It may happen, it's a very slow process. You see, the entire oscillation from the highest point to the lowest point may take about 40,000 years. And that would mean that in those 40,000 years, the tropics would expand and contract, isn't it? By definition, if this angle was to be more, the point at which this ray, sun's ray, going and meeting the center would be at a further southern location, isn't it? So the same would happen for the northern location also. And therefore, what it would mean is that tropical belt would widen and shorten in this frequency of once in 40,000 years, so to say. Now, that has a profound effect on the climate, long-term climate shifts. There is another effect, that is the ellipticity changes. The ellipse becomes a little elongated and then becomes a little circular during a period of, say, 100,000 years. So during this period of about 100,000 years, again, you will have a difference in the distribution of solar radiation. Okay. In the first one, you saw that the solar radiation distribution as per the latitudes, and here it is the solar radiation distribution by time. Now, these are the two basic things that control long-term climates, and we know that they result in ice ages. More on that is certainly not to be discussed over here. But please remember that the axis defines the season as it is today, and if the axis were to change in various ways, they would define the climates within which the terrestrial climates would have to be confined. So one end of the terrestrial climate is the ice age, and the other is the glacial period, and the other is the interglacial period. The frequency has varied with time, and in the last 2.5 million years or so, the frequency has remained close to 100,000 years. Okay, before that, it was a little more frequent at 40,000 years for the earlier 15 million years or so. Now, that is the long-term climate phenomenon. Right. Now, let me come to this diagram. This is a cartoon, so to say, as the terminology goes nowadays. Let me just shift this one moment. Yeah. sorry. So look at this, the cartoon of the sun. This is the Earth, and casting a shadow, so to say, over here. So what would the sun do is it sends radiation, and this radiation falls on this hemisphere, and it doesn't fall on this hemisphere, and it casts a circular shadow. So 4 pi r square r being the radius of the Earth. Okay, that's the area, which represents how much the Earth has absorbed. Okay, that represents how much the cross section of the Earth that has absorbed the heat coming from the sun. Now, look at these figures. Radiation emitted by the Earth. Okay, now that the whole sphere does emit, although a part of the sphere will receive, but the entire sphere will radiate. Now, apply the Boltzmann's law that you had done on the last lecture, and 4 pi r square is the total area. So you had multiplied, remember in the Boltzmann's law, area multiplied by sigma T to the power 4, and this T is called effective temperature. Effective temperature. Although this is an imaginary situation, it doesn't have an atmosphere, and therefore this is an effective temperature. If the Earth did not have an atmosphere, the Earth would radiate this amount, and the Earth would be at a temperature TE. This is one part of the equation. That is the part that is absorbed. And what is absorbed is proportional to the surface area, isn't it? Because this is the amount of radiation that has been removed from the stream. Removed from the stream means that it has been absorbed by the Earth. You can come to this conclusion using calculus by taking the angles and integrating the angles from 0 to pi by 2. But this is a very simple way of coming to the same answer, which says that this diagram shows that this is the amount of radiation that has been removed from the stream, and it is obviously due to absorption. So how much will it be? It will be proportional to the area of the circle, and that is nothing but pi re square. Now, so this left-hand side and right-hand side, when you equate, this is called the radiative equilibrium. Now, when you simplify this, it gives you the temperature at which the Earth would have been if it had no atmosphere and if it was in a radiative equilibrium. So what does it come from? Where does it come from? It simply is dependent on the Boltzmann constant for black body, and then on the reflecting power of the Earth's surface. So only these two things will determine the radiative balance condition. This is the simplest possible thing, but we know that the atmosphere complicates the matter a little bit more. And now this is a restatement of this equation, which says that the global average incident sunlight should be this portion. Okay, that means the absorbed part has been taken into consideration, and therefore this is the Q0 by 4, 340 watts per square meter, provided that the radiance of the incident light is 1360. That means you hold a surface perpendicular to the sunlight, imaginary surface, it will receive this. Okay, and when you average it for the whole sphere, what you get is 340 watts per square meter. Now, this is how you find out TE, and let's see what the values are. We know Q0, 1360. Let's assume a reflecting power of 0.3, which is roughly the average of the surface in most places, solid Earth surface, and Boltzmann constant, 4 into Boltzmann constant, and you get a value of 255 degrees Kelvin. Now, let's not judge whether it is high or low or something until we find out the case, what the temperature would be in radiative equilibrium when there is the atmosphere. All right. So, if the Earth's surface was only oceans, what would happen? is this albedo would be different, isn't it? It will become much, much less. So in that case, if this becomes less, what happens? 1 minus that becomes more. Therefore, TE becomes a little more. The TE becomes 274 degrees. Okay. So what the planet is composed of, that dictates under equilibrium conditions, radiative equilibrium conditions, what would be its temperature, equilibrium temperature. This is just demonstrative of the fact of the principles. The moment you put an atmosphere to it, these principles have to be modified. And obviously, there you cannot define a TE as the effective temperature. We need to define the temperature of the atmosphere, the temperature of the Earth, and that is where the notion of the greenhouse effect comes in. All right. Now let's see what will happen if the atmosphere was there. Now, if the atmosphere was there, the atmosphere is a fluid. There's amount of heat being deposited on the ground, which is sunlight absorbed, is the amount of heat which is deposited on the lighted hemisphere, and that would heat up the ground. And if that heats up the ground, that would give radiation. So radiation coming from the Earth would be then, if there was an atmosphere, the atmosphere would absorb. And if the atmosphere absorbs, it will also become a radiator, because it will radiate on either direction. So we need to consider that if the atmosphere was there, it itself becomes a radiator, and a part of the radiation comes back to the ground, and a part of radiation goes back to space. But remember, this is the planet Earth, which is receiving energy from the sun. And so the moment you are in a location which is outside the atmosphere, the balance has to be restored in the manner that has been restored here. Inside the atmosphere, the balance will be different. The temperatures would obviously be different. Now, this is something that you need to remember, that the radiative equilibrium conditions depend on the temperature of the bodies. And if there was an atmosphere, the atmospheric temperature would alter this equilibrium. In other words, would alter the temperature at which the planet comes to an equilibrium. This is one important thing, if the atmosphere was there. But also, if you look at the dynamics part, apart from the radiation, if you look at the dynamics part, the atmosphere is a fluid. It will break into convection, because if there is surface heat to be transported away from the Earth, then, and if it was a fluid, the fluid molecules would rather move themselves and carry this heat. Okay, that's a far more efficient process than the radiation. So ultimately, what will happen is the amount of heat carried away or transferred from the Earth's surface to outward would depend upon how much heat is being carried away by this convection, and how much is being done by the radiation. Instantly, both of them will come to an equilibrium, the convection and radiation. Okay, they will come to a equilibrium condition, and that is called the radiative convective equilibrium, which is the real case. Pure radiative equilibrium inside the atmosphere is hypothetical. Okay, radiative equilibrium, if you have to see, you have to go outside the Earth's atmosphere. But if you are inside the atmosphere, you would rather look for an equilibrium condition, a thermal equilibrium condition, where both radiation and convection are connected. So this is where the dynamics gets linked to the physics of radiation, is that the amount of heat that is available to convection is decided by radiation. The radiation itself is transporting a certain amount of heat. This will be the subject of our third lecture, and we call it the equation of radiative transfer. Sorry, it will be probably the fourth lecture. Yeah. So we will discuss that in a little more. Let us now confine ourselves to seeing by the effect on this temperature, that is the effective temperature, what is the difference when the atmosphere comes into play. Well, obviously, the diagram will look a little more complicated. And what is happening here is sunlight is coming, is going, and here is the atmosphere drawn here. Try to imagine the situation. Atmosphere is drawn over here. So in the earlier situation, it was only the reflectivity of the ground that was important when the atmosphere was not there. Even now, the reflectivity of the ground is important. But what is being added? What is being added is the atmosphere's effect. So the atmosphere absorbs this radiation coming out from the ground. Clear? And when it's absorbing, it will radiate itself outwards as well as downwards. So when you started with, I mean, it's a thought experiment that the effect of the atmosphere is not yet to be considered. When you imagine that the absorbed radiation from the sun is the cause of this radiation, what did we say? That this temperature would be TE, isn't it? TE. But when the atmosphere comes into being, this TE has to be replaced by the surface temperature, because now there's a notion of a surface and an atmosphere. Clear? There is the amount that is absorbed, we can easily calculate using the Kirchhoff's law. So let's do that. But please remember, please try to guess what is expected out of it. What is expected out of it is the atmosphere returning a part of the heat that this was radiating out. Automatically would mean that TS will have to be larger than TE, isn't it? It automatically means that now it is getting more energy than it was getting earlier in this case. It is getting energy from the Earth's atmosphere also. And this is the greenhouse phenomena. And let's see the numbers. How do they turn out, the numbers? If this being the Boltzmann's radiation from the surface, that means the Earth is at a temperature Ts, and we have now brought in Ts because we know physically that Te is no longer valid, and therefore it is according to the emissivity of the atmosphere, the amount gets absorbed. This is the Kirchhoff's law, correct? Kirchhoff's law says that you multiply this amount by the emissivity, and what you get is the amount of radiation absorbed by the atmosphere. So this eta is the emissivity of the atmosphere. This radiates according to the temperature that the atmosphere reaches, and that temperature cannot be Ts. Okay, that temperature cannot be Ts. That is because it's a separate body intervening between one solid body and space. Obviously, there has to be a gradient of temperature. And if that is a gradient of temperature, Ts is what we start with, and Ta is the intervening temperature. The atmosphere is at a temperature Ta. Now, again, the emissivity has to be multiplied. Can you guess one more thing? That the moment we brought the emissivity is fraction. Now, if you bring in this fraction, you're not dealing with black body anymore. You are dealing with a gray body. And so this is the gray body atmosphere. So this is called a gray approximation. And you've also seen that gray should be only a window, a possible window. Okay. So it is also sometimes termed as gray window approximation. Okay, it's a gray window approximation. And so when you have this condition of a gray window approximation, we are going to rewrite the laws of radiation balance. This is our endeavor. This is our purpose. Right. Now, so emitted radiation would be equal to this according to the temperature of the atmosphere, and that would go out, that would also come down. So this amount is getting to 1 of this, isn't it? Q0 by 4 into 1 minus alpha. So that is the one that the sun is giving you. The one that the left hand, you see, equation. I think the sun is giving you. So that has two components. One is what it is losing, the Earth is losing, okay, according to the surface, and what the surface is gaining in terms of the atmospheric radiation that is coming into it. A very simplistic way of writing this balance equation is that this is the amount that is going out, 1 minus this was going out, isn't it? If this is the amount absorbed, then 1 minus epsilon would be the amount that it is being re-irradiated, that is going out, so to say. Correct. This plus this is equal to this. Now, this therefore defines that TS4 is always a positive quantity. TA4 will always be a positive quantity. And therefore, we will get an opportunity to tell which is greater and which is less. Okay. Now, this is equal to sigma T e to the power 4, which was the balance if the Earth's atmosphere was not there. So the Earth's atmosphere being here brings in two radiation streams, one outward going and one downward coming, both in the window region of the spectrum, that is the infrared region. Right. Now let me just put this into the equations. At the top of the atmosphere, that means over here, you have to decide a balance. And at the bottom of the atmosphere, you have to define another balance. A single balance equation is no longer valid because the atmosphere has come into existence. Now, when you write this, this is at the top of the thing. This is the one that is valid. What it is saying is energy coming from the atmosphere and energy coming from the ground, which is depleted by the atmosphere. Okay, this is energy coming from the ground, but depleted by what the atmosphere has absorbed. This is what this terms means, and this is what is coming from the atmosphere. Remember, what this has depleted is at a temperature Ts. What it has gained is at a temperature Ta. So the two are definitely never the same. Okay, the two will definitely never be the same, and that is the entire reason why the atmosphere goes into a dynamical situation. So the whole story lies in the fact that what is removed by the atmosphere from this stream is not what the atmosphere gives back. Okay, so at the top of the atmosphere, we have this relationship, therefore, and at the surface, we have this relationship. At 1 minus of this, which the sun is giving you, plus what the atmosphere is giving you, that is what the Earth has to radiate out. The solid Earth has to radiate out. Otherwise, it will not be in a balance. Right. Now, these two equations, please remember them. Very easily, you can substitute this from the first into the second, and you can simplify this. Just simplify this. And as a ratio of Ts and Ta, you can find. Okay, you can find out the ratio of Ts and Ta. It clearly shows, because of this term 2 epsilon, the Ts has to be greater than Ta. Well, this, as I told you, is known as a greenhouse effect. A little bit more of this greenhouse effect we shall discuss just a little later. But for your convenience, please remember that these are the new balance conditions. How these new balance conditions have been arrived is that at the top of the atmosphere, you have what the atmosphere is giving you, that is one term, plus you have what the solid Earth is giving you, minus what the atmosphere has absorbed. So very easily understandable, minus what the atmosphere has absorbed. And what the atmosphere has absorbed, mind you, is not what the atmosphere is giving you back, because the temperature gradients are all different. Here, the temperature gradient between the ground and the atmosphere, and the temperature gradient between the atmosphere and outer space, they are different. And the difference in temperatures is what the amount of radiation depends upon, that is given by the Boltzmann's law. Right. Please remember, we have discussed this equilibrium only for the total radiation. That is, when it is integrated for all wavelengths. When you talk of the spectral terms, the equations become a little more complicated, and that is when you want to use it for remote sensing. When you want to use it for remote sensing, these equations have to be written in the spectral forms, and they don't look so friendly at that point of time. Right. Surface equilibrium similarly will reveal you a different condition, and that says that the surface equilibrium will tell you that this left-hand side value is the sum total of this, and that automatically means that Ts is bigger than Te. That's also pretty understandable. So the Ta, Ts, and Te, these are the three which are all different from each other. So if the Earth didn't have an atmosphere, it will fall to a temperature of what we derived at 255 degrees. Now the atmosphere has come, the atmosphere has assumed a certain temperature, and it has affected the surface temperature has now become higher than that. Let's see how much higher. We can find that out. We can find out how much is it, Ts. So you can use these equations to solve for Ts. And this is substituting Ta from 3 into 1. So from 3 into 1. Just substitute Ta in terms of Ts, and then you can solve for Ts. That's all. That gives you this. What does it depend on? Let's look at the right-hand side of this equation. What does it depend on? It depends upon the planetary albedo. Okay. Now, you talk of the planetary albedo. Very conveniently, I have shifted to the word planetary albedo. You're talking about the terrestrial albedo. Now, there's simply, the moment atmosphere is there will be clouds, there will be dust, there will be particles, air molecules. They will all add to the reflection. Okay, and that is where the terrestrial and the planetary albedos differ. When you talk of planetary albedo, you talk of the net albedo, which includes reflection from clouds, which includes reflection from air molecules, which includes reflection from particulates, dust particles, and many other aerosols. So that is one thing on which this depends. If alpha were to become smaller, become less, Ts was to become higher. Okay, so if the Earth was reflecting less, this would become higher. How can you have a situation where the Earth was to reflect less? Well, if there were no clouds, one thing, or if there were less clouds. So you can very well understand, if you forest the region, the green cover will reduce the value of alpha, and all of these can increase the value of Ts. Okay, so this is something that these are called external factors that cause a change in the shift of the equilibrium condition, and by changing the albedo. The albedo can now be changed by parameters in the atmosphere as well as by parameters on the surface. And the whole climate system, which is an interplay between the atmosphere and the surface, that is what the climate system is, makes it so intricately related to each other. And that is why you cannot say that the Earth's albedo will change by changing the surface temperature or changing the atmospheric temperature. How the other elements will react, how the clouds will react, depends upon the vertical gradient of temperature. Then how the aerosols will react depends upon the surface velocities of winds that are generated. Then how the land cover will react will depend upon the moisture balance at the ground. Now, all of these factors, they make the system intricately coupled to each other. And therefore, the planetary alpha cannot be simply prescribed. It has to be decided by the models that represent the interaction of various subsystems in the climate. Clear? You cannot simply plug in a value of alpha by saying that I have changed the forest area, and that's why the alpha has changed so much, and that will be the effect on Ts. Well, that really never happens, because any change in Ts caused by changing, say, the forest cover or so, will bring about changes in aerosols, will bring about changes in the cloud cover, and therefore what you get at the end of the day is a TS depending upon the entire response of the climate system. Okay, now this single equation has got this whole history hidden inside it. If you unravel the way the climate system works, you have to really look at the gross picture, how it will affect the gross picture. Looking at it microscopically from one point of view is not enough. So this is one thing, one way of looking at this equation and trying to interpret it. The other way is to look at this epsilon. What does this epsilon depend upon? And the emissivity. It's the deviation from the black body to the gray body, which is obviously caused by the molecules of the atmosphere and the constituents of the atmosphere, so to say. Not just the molecules, but the constituents of the atmosphere. So constituents of the atmosphere, changing moisture content is one of the simplest ways you can imagine. By changing the different trace gases, there is another way you can look at it. By alteration of the climate of the clouds is another way of looking at it. So if the emissivity changes, that also will change the surface temperature. So you see, planetary albedo and emissivity, they come from the composition of the Earth's atmosphere and the ground. So these are therefore the controlling factors that determine the relationship between Q0 and TS. Q0 is something which we are given for granted, coming from the sun. TS is something that is produced out of the climate system after intricate interactions. So the relationship between them in a gross sense is summarized in this particular equation. Right. Now, let's do a little bit of computation because we know some of these values and we can plug in. We can take an alpha to be 0.3 just for illustrative reasons. And this is a value that we know, Q0. Now, TS as observed across the globe, say 288 degrees Kelvin as on date. Suppose you plug in this value of TS, you get an atmosphere at 242 degrees Kelvin. You can do this exercise either way. This exercise was done in this way, is given TS and you find out TA. It could be done the other way around. You could find out the mean temperature of the Earth's atmosphere and that would give you the TS value. But from here, if you know this and if you know this, you can find out the emissivity. Okay, you can find out the emissivity. That means experimentally you observe the surface temperature, experimentally you observe the mean atmospheric temperature, use this value of alpha, use this value of what the sun is giving you, and you come that the emissivity of the Earth's atmosphere is 0.78. Now these values are just for your appreciation. I mean, these values, how close they are to 1. Is it 0.5 or is it 0.8? So 1 would have been a black body. Okay, so this is not too bad. It's a gray body nevertheless, but not too far removed from a black body behavior. Now, it is to be noted that with this condition of radiative equilibrium, TA will rise in response to TS. Now, and vice versa. So this is the line that we can take home from this equation, is the relationship between TS and TA given the emissivity changes. And that is the reason why we are looking at the composition of the Earth's atmosphere in so much of detail. You're measuring trace gases, you're measuring aerosols, everything. And that's with the implicit understanding, not explicit though, with an implicit understanding that we are really understanding what is the emissivity change. Right. Yeah. Now, without the atmosphere, TE was the temperature. It would have been the surface temperature, and that we know is 255, right? And 288 is with the atmosphere that you have got over here, 288. Please remember that this is subject to whatever presumed values of alpha and epsilon we have. In future, it is bound to change because both alpha and epsilon are changing. And therefore, for an instructive purpose, let us take this 288 degrees. Minus 255 is what it would have been if there was no atmosphere. This difference to you should be the contribution of the atmosphere in warming up the surface. And therefore, this is equal to 33 degrees is the greenhouse effect. So how much is the greenhouse effect of the atmosphere? Is Ts minus Te. Right. And Te was obtained from very simple considerations. And Ts you can obtain by measurements across the globe and averaging them. Or if you're able to get the new value of epsilon and alpha, again observationally, then you can use this relationship to give you the new value of Ts. And so the greenhouse effect is dependent on alpha and epsilon. This is the bottom line. The greenhouse effect is dependent upon the alpha and epsilon, which is representative of the Earth's atmosphere at a particular point of time. Now, 3 persons have raised their hands. Yes, please. Now, I think I should be taking their... can we take their questions right away?
Write the questions on the chat box because we can't see who are the people who have raised their hand.
I couldn't see the people who have raised their hands, yeah. But
they cannot speak. And they cannot speak because we can't hear them.
Oh, God. I was expecting there would be some hands raised somewhere.
They have to write the questions on the chat box that we have already told them many times. That
let me see if in the chat box I can find questions.
Now we will read for you at the end when the lecture is over.
Okay, okay, right. Okay, right. Now, the difference between the emission from the surface and the top of the atmosphere, that is also important, isn't it? The surface emits this much, Ts to the power 4 into sigma, which happens to be 390 watts per square meter. And the top of the atmosphere is when you use this value. And this is equal to, when you use epsilon as 0.78, is equal to 240. Now, this difference between the surface and the top of the atmosphere of the amount of radiation is the radiation that is forcing the greenhouse effect. Therefore, it's called, in short, the greenhouse forcing. And this greenhouse forcing is of the order of 150 watts per square meter. Yeah, subject to changes in the future or subject to more rigorous evaluation. You come to this notion of the ratio of these two numbers. This 33 that we have got there and 150 that we have got here is the per unit greenhouse forcing. What is the greenhouse effect? Okay, per unit greenhouse forcing. What is the greenhouse effect? In other words, how sensitive is the surface temperature to the greenhouse forcing? And the greenhouse forcing is a function of the atmosphere. Okay, so what is the sensitivity with which the surface temperature would change if the atmosphere were to change the greenhouse forcing? And this ratio, well, roughly comes out to be around 0.2, 33 by 150. It is said to be the climate sensitivity. Here, climate is the proxy variable for climate here is Ts. Okay, so it's actually the sensitivity of surface temperature with respect to the greenhouse forcing. And the greenhouse forcing is the distance, the difference in the emission from the surface and the emission from the top of the atmosphere. All right. When we have a little more complicated situation, let me have it over here, that there is an aerosol layer. When there is an aerosol layer, what will happen is, if you look at this diagram, the aerosol layer will absorb something. Okay, and 1 minus of what it has absorbed will come out of the aerosol layer. That's one thing. Second thing is the Earth will reflect. And so there is a alpha value to it. Okay, the albedo. So A value is the absorbance. Alpha value is the albedo. These are the two additional factors that are coming in. Now let's see, is it really practical, or is it realistic to assume that the aerosol layer would be hanging above the Earth's surface? Now, this is usually the situation because in the boundary layer below this, aerosols are removed by dry convective currents. They are impacted against the ground back again. And so to say, they are diluted by convection. That is one thing. And above a certain height, they don't go because they have not been injected beyond a certain point. This aerosol layer obviously hasn't grown in situ. This aerosol layer has been injected by dust-raising winds predominantly, or huge fires, or sometimes even volcanic eruptions, which would have injected aerosols. Above this layer, therefore, there will be very few aerosols. Below this layer, there will be very few aerosols. So this is a hanging layer of aerosols which can be transported over long distances and which have the possibility of creating a regional effect. So a regional effect can come from this kind of an aerosol. And we have noticed that on the fringes of the large deserts, you always see a cloud of aerosol which has come out of that region along with the subtropical high, the winds of the subtropical high, and spread into the tropical regions. That is a phenomena which we have often seen. And they usually happen after large-scale convection, dry convection, has kicked up a lot of dust. And this dust gets carried with the winds. On the north of the subtropics, it goes from west to east. On the south of the subtropics, it goes from east to west. And this is how the dust is transported to a large area and subjecting a large part of the globe to the radiative effects of this kind of a phenomena. Now, fine. This is again the energy coming from the sun. A part is reflected by the aerosol layer, and so it goes back. The remaining part, 1 minus of that, is the one that is coming into this dust layer, and out of that a fraction A is absorbed. So obviously 1 minus A is what emerges from the bottom of this layer. Clear? Now, what is reflected from here is a fraction of this that is coming in, and alpha fraction is reflected. So this ray that you have seen here, this represents alpha into 1 minus A into 1 minus RE into Fs. Fs is the downward coming solar insolation. The same phenomena happens again, and therefore you have part of it absorbed, part of this is absorbed. When a part of this is absorbed, after a part has been reflected from the bottom, okay, a part of it has been reflected in the bottom, and the remaining part goes in. And as the remaining part goes in, a fraction of that is absorbed again. And therefore, this is a geometric progression. You can consider as many terms as you like, but they will all be converging into a solution. That is important, because each time the values become lesser and lesser and lesser by a multiplicative constant. That is important. And at the end of the day, this is what comes out. Alpha into 1 minus A square into 1 minus RE square as a fraction of what has been coming down. So you see the entire planetary albedo can now be defined, isn't it? Entire planetary albedo can now be defined. Now, in a simplified case, when a equal to 0, suppose, or very close to 0, you can simplify this. You can simplify this geometric series, and you can take the first few terms, which says that this is equal to RE into Fs down into alpha into 1 minus RE square, plus this is just a simplification of these terms with the assumption that A is equal to 0. And also assuming that RE is pretty small. Only the dust does not reflect a huge amount, okay? So pretty small. That means this is about equal to 1%. Then all in terms of RE square can be neglected, and you can write Fs going out, okay? Fs going out to be equal to a function of Fs coming down. And this is the function, okay? This is the function. It is a combination of the reflection of the dust. It is a combination of the reflection of the ground, and then it is a combination of the interplay between the ground and the dust, okay? Interplay between the ground and the dust. So this complicates the picture a little bit, but nevertheless, you can appreciate that the planetary albedo is not just what the outer space is looking at the planet. It is looking at the aerosol layer. So if it was only the aerosol layer, it would have simply got Fs into Re. But it is also seeing the reflection from the ground as severely modified, and therefore reflection from the ground as severely modified. It is reflection of the ground is this one that is coming into this picture, plus this is the modification. What is the modification? Planetary albedo into this reflectivity, the product of the two reflectivities minus the twice of the reflectivity of the aerosol. So this is how you look at this equation in a simplified fashion. Just a sec. So you have this concept of an altered planetary albedo now. The earlier albedo from the ground was only alpha. And now you have this change of albedo, delta of albedo, that is coming from this ratio minus alpha. So how much has the aerosol changed the albedo? That is being answered by here. So this alpha is equal to Re minus this term, okay? Fs divided by Fs, Fs upwards and Fs downwards minus alpha comes to a simplified form in this relationship. So this is how the Earth's planetary albedo has changed. Now, does this affect positively or negatively is the second question. It comes from whether the right-hand side is positive or the right-hand side is negative. And the right-hand side being positive and negative is an interplay of these three terms, two of which are positive terms and one is a negative term, okay? If this negative term is higher than the sum total of these two positive terms, delta alpha is negative. In other words, the planet becomes more absorbing, okay? The planet would heat up, so to say. So in these circumstances, the aerosols lead to heating of the Earth's surface. So this is one thing. But if it is positive, like for instance, if the values, the composition of aerosols is such, and the ground over which these aerosols are existing, the alpha of that ground, if the interplay is such that this is positive, okay, so that these two terms are actually larger than this minus term, then this becomes positive. In other words, when this becomes positive, more light is reflected back to space. In fact, it will cool the ground. So the aerosols, with the combination of the ground, have the capacity to either cool the ground or heat up the ground. Okay, so they can either be adding to the greenhouse effect or be taking away from the greenhouse effect. Both of these are possible depending upon what is the absorbing power of the aerosol, what is the reflectivity of the aerosol, and also the ground on top of which they exist. That is also a very, very important. So the same aerosol over an ocean surface may be absorbing, but over a land surface may be cooling. Okay, so this is very important, that when from the subtropical high a huge aerosol cloud enters the Arabian Sea region, say in our area. In other areas, it may be over the Atlantic. Over the oceans, it may cause warming, but when it goes further and enters the land, it may cause cooling. Now, both these effects are possible from the same aerosol. That is simply because in these relationships, the underlying alpha of the ground comes into play. All right. This is something that in principle we have seen. We haven't worked out for any real aerosol, but these are demonstrative. These simple equations are simply demonstrative of a fact that we have known, that we have discussed, and that we keep talking about, that the aerosol layer can either warm or cool, depending upon what the aerosol is. And now we know it's not only on what the aerosol is, but on which surface is it overlying. So please remember that this is the added information that we are getting from these equations. Now, similarly, the short wave flux at the surface, you can work out at the surface, which is Fs dash. This will no longer be Fs downwards, but it will be a little less than that. How much less than that? That which is reflected, as well as which is an interplay between this reflection and the ground reflection. Okay, that means the amounts that is coming down as a result of the fact that the aerosol has reflected a part of the outgoing radiation. Okay, here the aerosol has reflected a part of the outgoing radiation, and therefore what you get at the ground is a combination of one is what the sun is giving you minus what the aerosol has reflected back plus alpha into Re as an approximation. Now, now in this case, it is said that it is seen that the solar input to the surface is always reduced. Now, this is very important. The solar input to the surface is always reduced. That means every aerosol, whether it is absorbing or it is reflecting, will actually cool the Earth's surface. Forget about the planet. Look at only the Earth's surface. The Earth's surface, the radiation, as long as it is removed from the stream, which is that stream that what the sun is giving you, either it is reduced by reflection away from the aerosol layer, or if the aerosol layer absorbs it, even then it reduces it, isn't it? So the surface will always have a reduced flux, but the planet as such can sometimes have an added flux. These are the two important things to remember. So the forcing of the aerosol would always be to cool the surface, but it can also be to cool the surface and warm the aerosol layer. Now, I'm sure you are arriving at a logical extension of this statement. I'll make the statement again, and please try yourself to come to this logical question. The effect is to cool the ground. And on top of that, to either warm the air above it or cool the air above it. Now, if it cools the air above it, you have the normal lapse rate situation. But if it warms the air above it, you have an inversion situation coming in, isn't it? So, if the aerosol absorbs more and adds temperature to the upper layers, automatically it means that it is stabilizing the troposphere. If such an aerosol is absorbing, it is only going to stabilize the troposphere. Why? Because it has added temperature in the situation, not always, but in the situation when the aerosol layer is absorbing, highly absorbing, it will add heat to the upper layers, and always it will cool the surface. Always, that is what we have seen. It will always cool the surface, but it will. There are opportunities of this layer to warm it, and when it warms, it causes reduction in the vertical lapse rate. And reduction in the vertical lapse rate is stabilizing. So what is the effect of this aerosol on the climate through the hydrological cycle can easily be understood. All right, it slows down the convection, and this convection leads to rainfall. And so it has a it has a prospects of a profound influence on the rainfall climatology also, provided it absorbs enough. Provided it absorbs enough. If it doesn't absorb enough, and that absorption also is tempered by the albedo of the ground, that means this condition has to be satisfied. Provided all those conditions are satisfied, certain aerosol layers can have a profound effect on the climate system by modifying the convection, the intensity of convection. As an indirect effect, it can have an effect on the lifetime of the clouds. The clouds, rather than coagulating and giving rain, may spread out and live in the atmosphere for a longer period of time, increasing the albedo of the planet, decreasing the amount of rainfall. So that's a secondary effect. Okay. Now there can be many such secondary effects that you can think of, but the aerosol undoubtedly complicates the Earth's climate system by, first of all, reducing the amount of energy coming at the surface, by also sometimes stabilizing the atmosphere and affecting the hydrological cycle. So these are the profound influences that aerosols can have in practical life. The most absorbing aerosols are the ones that are that have carbon compounds, preferentially the smaller chains of carbon molecules, say up to 4 carbon atoms in it or 5 atoms in it. They are classified as elemental carbon, and then you go to organic carbon as you longer chain of carbons, and they can come from combustion. Like large amount of forest fires can give you unburnt carbon. Why unburnt carbon from these forest fires is simply because in the middle of the fire, not much of oxygen is reaching, isn't it? The fires are so large that it is starved of oxygen in the middle of it. And in that case, the entire organic substance will not burn. And if it doesn't burn, it leaves a large number of carbon molecules of various kinds, of which elemental carbon is a huge proportion. And if this elemental carbon comes out of such large fires, automatically they would stabilize the Earth's atmosphere, because elemental carbon is absorbing. All right. Now, this is how the mineral aerosol behaves is very complicating. It depends upon which desert area it comes from. But yes, the mineral aerosol does also absorb a little bit in the short wavelengths, but not as much as this elemental carbon. So elemental carbon or soot is therefore said to be warming the atmosphere. Okay, it's said to be warming the atmosphere. Now, these are some very simple generalizations that we have drawn here. Now, when the absorbance is a little small, you can modify these equations and you can modify this relationship. But that is incidental. I mean, I wouldn't lay much importance. Most of the phenomena that we have talked with come from these two equations, with these two presumptions. And that is very, very important for us. These are the two effects that we have seen an atmosphere brings in terms of radiation effects, and in terms of how the radiation effects have the prospect of changing the hydrological cycle also. Maybe I will like to finish it here, and I'm sure there'll be questions. I think that this is the time to address these questions.
Yeah. Now we can start the question and answer session. Dr. Rohini, you can read the questions.
Yeah, sir, actually there is one question. It's about asked by an anonymous attendee. He asked, is Earth a black body? That's
is the Earth a black body?
Yeah.
Yes, it's very close to the black body, the solid Earth. The important thing is that the solid Earth is at a much lower temperature than compared to the sun, which is the other black body that we are looking at. Okay? And therefore, anything that is in equilibrium, even the atmosphere would have become a black body if it was in an equilibrium. I mean, if the temperatures weren't fluctuating in it, if there is a way of transporting the heat instantly from that particular point where the heat is deposited, that again behaves like a black body. So relatively, the Earth is a blacker body than the atmosphere. And both are gray bodies, so to say. But the Earth's solid surface, solid Earth, is more of a black body. That's all.
Sir, there is a comment from L10. The lecture is very interesting and educative. So he has asked you if you can also include the reference materials or books, so that
Sure,
we would
absolutely.
like to go in more details about this.
Definitely. I will give all the references, yes. When
Yeah,
I give
it was very, yes, please continue, sir.
Yeah, when I will give my this abstract of this, I'll invariably add the references to that. Definitely.
Yeah, so the lecture was really very useful. Especially hello.
Oh, thank you for that. And I hope it makes sense.
Especially the aerosol part, which was, I work on aerosol, so it was really very useful, sir.
No, is there a specific question? I'm sorry, I didn't get it.
No, I think there were only two questions,
Okay.
one comment and one question. So maybe
Okay.
Everyone is asking for books specifically. So
I know. Yes, sure.
I think they need to read a little bit.
Yes, I would definitely send across to you the list of references. But until you get them, you use these keywords, aerosol, radiation, then any of the keywords that your planetary albedo and things like that, and you can ask get a lot of material from the Google itself. But it's important that you fire in the right kind of keyword. Yeah, you can pick up the keywords from the lecture and fire them until you get the textbook sources. I will give you that also.
There is one book, this Murray Salvi. They offer some topics of radiation, atmospheric. That book is, I think, freely downloadable from internet.
Okay. And I believe that this book by Poltridge and Platt on atmospheric radiation, which deals with it from a very, very elementary point of view to a little more advanced also. So both the things are given here. We are only looking. Poltridge and Platt.
Book, Atmospheric Radiation by Liu. That also.
Oh yes, that's a very good book. Yes.
Standard book, yeah.
Yes. Most of the books that are standard, they have elaborate mathematical derivations and mathematical computations. So they should be studied a little later. The easier ones we could start with. I mean, those who are already advanced would definitely go in for the more standard textbooks. But I, for one, thought that Poltridge and Platt's book on atmospheric radiation is a very good book to start with.
Okay.
But anyway, I'll send that in writing. Yeah.
Yeah, I don't know if it is a comment or a question, but there is one more. Aerosol is a very influencing factor for climate modeling. Maybe they want to put a comment.
Yes, true. We just got a glimpse of it by even more a very coarse way of looking at the processes. We saw that they have profound influence on the climate. Difficult to model though, but still, because we are talking about the wavelength integrated parameters. But when we know most of the material, they are very selective. So there are large spectral absorbances and spectral reflectances, both. And so we need to look at the spectrum, write all these equations in the spectral form.
One more question has come now. How the aerosol optical depth can change the trend of rainfall? Okay.
Aerosol optical depth is nothing but how much of aerosol. Okay. This diagram is still on view. The amount of aerosol is the aerosol optical depth. I will cover that in the last lecture, but it's very the simplest way of looking at it is all these effects will be less if it is optical depth is less, and if the optical depth is more, all these effects will be more. That's pretty obvious. Okay, aerosol optical depth is simply the number of aerosols is proportional to the number of aerosols that the light beam is going to encounter along the path.
Yeah, sir.
And if I am correct, there were some model projections, especially for the rainfall. So when they include the GHGs, the rainfall showing increasing trend. But when they include anthropogenic aerosols, it was showing decreasing trend. These were the results actually from papers I read. So in that way, these anthropogenic aerosols particularly, they play a key role in deciding the trend of the rainfall also.
Absolutely, you're right.
Yeah.
In fact, the anthropogenic aerosols mostly, unless they are coming out from coal-fired emissions, which give a lot of sulfate aerosols, the sulfate aerosols are not absorbing. Okay, they are more reflecting. But all other industrial aerosols that come from combustion, some large forests are also, partly anthropogenic, because human intervention has caused those huge forest fires. But not all of them, true. But then the bigger source is from our industry, from our vehicles, unburnt carbon coming out. They have a lot of absorbing power. And if they have a lot of absorbing power in the shorter wavelengths, automatically you have this phenomenon what we have discussed coming in. And so the anthropogenic influence on the climate is therefore pretty large through the aerosols.
One more question. Could you shine some light on the aerosol components, PM 2.5 and PM 10, and how they are characterized?
PM 2.5 and PM 10. Okay. Now, PM 2.5 is said to be the respirable range because that is a particular size which cannot be blocked by the airways. Okay. Larger than that is usually blocked by the curvature of the airway, our nose, so to say. The curvature and the mucus that there is inside, that causes the aerosols to be captured if they are more than 2.5 microns in size. But less than that, they enter the lungs, and therefore that's one aspect. Now, what these aerosols are that are entering the lungs becomes important in terms of health effects. They could be pollens, they could be allergens, they could be acid particles causing damage to the tissue. They could be organic particles containing benzene, causing accumulation, and then therefrom carcinogenic effects. So it all depends upon what these aerosols are chemically, what will be the effect. But the important thing is, if they are drawn into the lungs, being less than 2.5 microns in size, all their effects are therefore to be seen more predominantly. Okay. If they happen to reside in large particles, these chemicals, then they are relatively safe from the health effects. As far as the other effects of nuisance of haze and other things, I'm not talking of, only the health effects. 2.5 and 10 is related to health.
One more, sir. In general, what is the ratio of PM 2.5 and PM 1 in the atmosphere? What is the most parameter contribute to the variations of the ratio?
Drastically it changes. It changes by more than 200%, 200-300%. PM 2.5, we presume comes from anthropogenic sources, and the remaining ones come from natural as well as anthropogenic. Okay. Now, PM 2.5 has got a longer fetch. That means it can come from a longer distance, because it takes time for small particles to settle down, so that can travel also more. So these are the various features that are associated with 2.5 and 10, and their compositions are taken to be anthropogenic if it is less than 2.5, and natural plus anthropogenic if they are more than 2.5. This is the general, but true. Every day the situation is different, the ratio is different, the effects are different. Okay, and as I told you, it can vary by even 200 to 300%. That means 3 times more of smaller particles can arrive on a particular day.
Yeah, I think that was a. So over to you, Dr. Krishna.
Thank you very much, sir. I think for giving a very wonderful lecture today. We enjoyed this lecture, and so I'd like to mention actually one important thing, one very interesting thing which we have analyzed from this lecture series. So as in the beginning of the lecture, I have told that the participants with percentage attendance percentage of 80% will be getting appreciation certificate. So we have just analyzed it. We found that there are 151 participants. They have attended the lectures with the attendance of more than 80%, and they are from 25 countries. So this is really encouraging and really inspiring us also.
Absolutely.
Like 151 participants from 25 countries, they have got 80% attendance. And there is one more thing which really made us very interesting is we found that there are 840 participants. They have attended at least one lecture. So this statistics really inspiring us, and it is a great motivation for all of us. And we really thank the participants for their patient hearing and their attending these lectures and making these lectures. And we are very much thankful to you, participants. Now, before going to this vote of thanks, we can have some panelists can have group photo. So I request the panelists to turn on their camera. Tyagi sir.
Yeah, Mukho, I think it was very well illustrated aerosol impacts on our atmosphere, the weather and climate systems. And also the questions answer session was very, I think, this time people became interested. And what we look forward is also that if we publicize more, the follow-up on the YouTube also will increase. So these are the treasures for a long time. Your talks and all that will be made widely used. And of course, the references, if you provide, it will be useful to the participants to follow it up. Thank you.
Yes, sir.
Thank you, Mukho.
Yes, sir.
Can you please turn on your video, sir? Tyagi sir.
Dr. Mohan also. Mohan, are you listening? Mohan is not there.
Yeah. Rohini, you also take. I'm also taking. Yes, thank you.
Okay, thank you so much for that.
By the way, today's video is not available on the YouTube immediately because it was not live streamed. So after the lecture recording is over, then we can upload it.
Yeah. So we had an issue with the Zoom. That's why we could not live stream today. Hope we will resolve this problem by next lecture.
Sure.
You can stop recording, right? Dr. Lakshmi now?
Yes, I will stop.
Okay, fine. Thank you so much.